This video is about chemical equilibrium, especially as it applies to gases. We're going to talk about this for Honors Chem. So we're going to go through this PowerPoint, do a few sample calculations. Just as a reminder that chemical equilibrium is where the rate of the forward reaction equals the rate of the reverse reaction. The rates are equal, but not the concentrations. Even though the concentrations remain constant, the rates are what are equal. So under the law of mass action, what we use to do the calculations, you can see that we have a reaction here and that the K, which is what we are calculating, is based upon products over reactants. Products over reactants. Okay, so the concentration of C and D and the coefficient, okay, becomes the superscript for both of these. Okay, just the same it would be in the bottom, the J and the K, which are the coefficients here. So hopefully that's a reminder of what, or of how we calculate K. We've calculated K before. If we did one practice problem, you can see that we're going to have these two products on top, the concentration of the nitrogen dioxide in the water with superscripts of 6 and 4 over the concentrations of the ammonia and the oxygen with superscripts of 7 and 4. And voila, there it is. On another note, I don't remember if we've talked about this, but what happens if you reverse the reaction? Well, if you reverse the reaction, the reactants become the products, and the products become the reactants. So everything just becomes inverted, as you can see here. Now the ammonia and oxygen are on top, because now with a reverse reaction they become the products. Alright, well, let's take a look at some key things when doing these calculations. First and foremost, only for gases and aqueous, not for solids or pure liquids, and that K will always have the same value at a given temperature. If you change the temperature, then you can change K, but that's the only way you can change K. And that K, when it's equal to 1, is in a perfect equilibrium. If K is greater than 1, that means it favors the products. If K is less than 1, it favors the reactants. Which makes sense because remember, concentration of the products over the concentration of the reactants. So if it's greater than 1, that means obviously there will be more products than reactants. If it's less than 1, then there must be more reactants than products. Okay, so I think that we should probably do a sample problem. In this problem, you can see that we're using the reaction of the N2O4, or the dinitrogen tetroxide, moving to the nitrogen dioxide. In this problem, you're given the K, and you are given the dinitrogen tetroxide partial pressure. So you're trying to find that of the NO2. Okay, so you have to do a little bit more manipulating of the equation. If we use our equation here, K is equal to the products over reactants with the coefficient becoming the superscript, and here's what the K is equal to, 0.133. So now we're going to have to do some manipulation of the equation. You notice that the K is now the PN2O4, the partial pressure of the dinitrogen tetroxide, is multiplied times the equilibrium constant, and that will give us the 0.360. And once we do that, all we have to do left is to, because we've got square, we have to square root both sides. We're going to square root this right here. This was originally squared, which means that it's just going to be the PNO2 is equal to the square root of 0.360, which is 0.600. Now don't forget, while K is unitless, the concentrations are not. And these concentrations, when dealing with gases, we don't do concentration, we call them atmospheres. Almost always in atmospheres. Okay. What I want to end with real quick is just a reminder about Le Châtlier's principle, that you can predict which way that the reaction is going to shift to respond to changes. And in basic concentration, it will shift away from the added component, or away from the whatever species is added, and towards. So if you end up removing some species, it's going to move towards that side. If more N2 is added, Okay, if we add more, remember our teeter totter, so to speak, if you add more on this side, it's going to shift back this way to get back to equilibrium. Okay, if the NH3 is removed, it's still going to move to this side. The piece that is the most difficult is talking about pressure and volume. If you increase the pressure, you decrease the volume, which means it's going to go to the side with fewer molecules of gas. Okay, so in this reaction, you see that we have a lot of moles of gas, but the side with the fewer molecules is going to be the NH3. It was N2 plus H2 goes to NH3, and this is an equilibrium, so air is going both ways. And if we're going to balance this, it was 2 on this side, but it was 3, so that was 4 total. So if we increase the pressure, decreases the volume, we're going to have more NH3 when all is said and done. And you can see that that is true. So we've got 6 over here, but before that we only had a couple. All right. Something else you should know, adding inert or uninvolved gases, it does not actually change the concentration. It may increase the total pressure, but does not increase the actual concentration or reaction between the gas particles. I think we just talked about this, so this is in the PowerPoint that you will be able to look up a little bit later. If you have any questions other than that, though, please don't hesitate to email or come in and see us. Thank you very much.